Alright, stats folks, are you ready for the fun stuff? Because this is the point when we start to transition to some of our somewhat more complicated hypothesis tests, a family of tests called ANOVAs. Now, again, if you hopefully are familiar with the 5 steps at this point, not just what happens at each step, but why we do it, that overall framework, you should find this pretty applicable to these new contexts. But a fair warning, this is material that oftentimes students find a little intimidating at first. I can tell you that it's not as complicated as it will initially look and maybe feel. The entire ANOVA boils down to just calculating two variances and dividing. That's the heart of it. That's it. But again, it can seem pretty overwhelming at first. It can seem more difficult than the other material. But please bear with me. Rewatch, review this stuff as many times as you need to, and make sure, of course, that you get practice working the actual steps in this kind of framework. But without further ado, let's jump into the fun stuff. So, quick recap again, we have 4 hypothesis tests under our belt at this point. We have 2 that are applied to what are called single sample situations. We get 1 sample of scores, compare it to a population that we know something about. If you know the standard deviation, you run a z-test. If you don't, you run a single sample t-test. And again, it's a very good idea to keep track of, in some kind of a flow chart, the decisions that you will make and the things you will look at to choose hypothesis tests. The last module was on comparing 2 samples to each other. We had 2 different 2-sample t-tests. If we had a between participants design, we'd run an independent samples t-test. If we have a within participants design, or what are called matched or paired participants, even though, again, we won't be discussing those in this class. We won't use those as examples. So for this class, if it's within participants, we use a related samples t-test. So those 4 tests, 2 of them cover single sample situations, 2 of them cover 2 sample situations. But what if we wanted to measure more than 2 samples at once? What if we had more than 2 groups of scores that we wanted to compare? Well, let's look at sort of a research question. Let's say somebody's interested in science of happiness, that kind of stuff, and they want to measure self-esteem in different North American countries, figure out which one has the best. So we want to get a sample from USA, we want to get a sample from Canada, we want to get a sample from Mexico. Again, notice we'd be making conclusions about the populations of these countries, but we'd be basing it on a sample. Either way, we have a situation where we want to wind up with 3 groups of scores instead of 1 or 2. So how could we address this? Well, we really could use different frameworks that we've already practiced to answer these questions. We could just run independent samples t-tests. They only work for 2 samples at a time, but you could just run a separate test for each possible pair of samples. You could run 1 t-test for the US versus Canada, a second for US versus Mexico, and a third for Canada versus Mexico. It would work. It would be a comparison of each of those 3 samples would each be compared to the 2 other samples, and you can see which ones were significantly different. There are some problems with this approach, though. Again, it's plausible, it could be done, but it's pretty impractical. First, it's kind of a pain in the butt to run, especially if you are doing it by hand like we make you do it in this class most of the time. So the number of tests that you'd need to run, there's a little formula. Don't worry about this formula. It's not something you'll be tested on. You won't even see it on the formula sheet, just for demonstration purposes. But if you plug in the number of means you want to compare, you can get, again, the number of t-tests you'd have to run to make all those comparisons. For 3 sample means, like what we just talked about, you have to make 3 different t-tests, 3 separate independent samples t-tests. Let's say we throw a 4th country into the mix. Well, we're going to measure some folks from Cuba and throw them in as well. Well, now we have to run 6 different t-tests to make all of those possible comparisons. Let's say we want to throw in a half a dozen or so Central American countries as well into that mix, and we wind up with 10 total sample means. Well, now I'd have to run 45 different independent samples t-tests all at once. Well, not all at once, but you get the idea. A lot of tests are required to make all of these comparisons. If you had to do it by hand, gosh, that'd be a whole day's work right there. But again, real researchers have computer programs that can do it for us. 45 isn't that much slower than running 1 for a computer. So does the cumbersome thing really matter? Well, maybe not if you're using software, but there's an even bigger methodological problem that's created. Remember when we talked about type 1 errors, those decision errors, those false positives. We said these are really, really bad in research. We want to minimize their probability. And we talked about the idea called alpha inflation. Basically, your alpha level is the likelihood of making a type 1 error, but just for a single test. When you run more and more and more tests at the same alpha level, the odds that there's at least 1 type 1 error in there starts to go up and up and up, to the point that it can get awfully high. And the problem is, of course, you can know that it's very likely you have at least one type 1 error there, but you don't know if there is one or not. And if there is one there, you don't know which result it would be. It really makes it hard to have confidence in your significant results when you know that the odds are very good that at least one of them is a type 1 error and you have no idea which one. So remember that type 1 error is our false positive. We reject the null when it's actually true. Those alpha levels were based on single comparisons. When we do multiple comparisons, like 45 different t-tests, the odds of at least one of them being a type 1 error goes up, up, up. Here's a little formula again. Don't worry about this formula. You'll never see it again, but it demonstrates basically the probability of at least one type 1 error. So with 3 comparisons and an alpha of 0.05, you wind up with about a 14% chance of at least one type 1 error, which again is semi-low, but it's a lot higher than that original alpha. When we're making 10 different comparisons, we go up to like a 40% chance of at least one type 1 error. And you don't even want to know about 45, but it starts to get awfully close to 100% that there's at least one type 1 error in there somewhere. So the more comparisons you run, the more this alpha inflation risk happens, in addition to just the clunkiness of running all these different tests. So here's my infomercial voice. There's got to be a better way. There's got to be a way that we can just kind of do all these comparisons all at the same time in the same format, in the same framework. Well, there is. That option is, and it's been written behind me the whole time, it's called an ANOVA, which stands for an analysis of variance. So an ANOVA is literally what the name says. You are calculating variances and you're analyzing them. It's an inferential stat. It's drawing conclusions about populations based on sample data. It allows us to compare means, but because we now have at least 3 means that we're interested in, we have to compare them indirectly by contrasting different types of variance. We'll talk a little bit more about that in the next couple of videos. Later on in the next module, we'll also talk a bit about when we actually have multiple independent variables, assessing how those variables maybe interact with each other. But that's a big to be continued there. So the first type of ANOVA, and the most commonly used one that we'll be talking about, is called a one-way ANOVA. So a one-way ANOVA is just a simple case where you have one independent variable or quasi-independent variable. Remember that population study, people weren't randomly assigned to grow up in Canada or the US. And you have 3 or more means that you're comparing. So one IV or quasi-IV, 3 or more groups. Your hypotheses involve 3 or more population means. So we run this with an independent samples design or a between participants design, and only one you might call a factor, a manipulated IV or pre-existing quasi-IV. So what's the variance we're analyzing? How does it all work? How does it fit into our framework? To be continued. Continue on to the next one, and we'll talk a little bit about the assessment of different types of variance and how that works. See you.